Hi. This fairly dank looking tunnel is potentially crucial for us as we look towards the future. This is a place whose name in Finnish, Onkalo, means the hiding place. What you're looking at is almost certainly the best and most highly developed disposal facility for high level nuclear waste that we have in the world. This is a problem which the disposal of this extremely toxic, extremely dangerous radioactive material is a problem that lots of countries around the world have to deal with. And as we'll see, they have to deal with it with their own geological resources. Britain doesn't escape this. So, what I want to do today is I want us to try and look at some of the geology behind nuclear waste disposal and to try and evaluate our own potential for disposing of this extremely difficult material. One thing I can say with some confidence, though, is that the solution shown here uh, isn't going to be acceptable. Now, to go with this lesson video, there's a number of other um, accompanying videos that you should watch. You'll see those come up in the usual red and yellow boxes. You may want to pause this video and watch those as we go through, or you may want to save those for the end. It's up to you. For this lesson, there are two handouts. There's one about the Onkalo disposal facility, and the other one about Britain's nuclear waste. Okay then, let's go. Okay, there are different types of radioactive waste. We call them low level, intermediate level, and high level. Low level waste is the bulk of the material. This could be clothing or machinery that's been exposed to radioactivity. We have a way of disposing of that. It's a place called Drigg, which is on the west coast of Cumbria, close to Britain, the centre of really Britain's nuclear industry, in a place called Sellafield, just up the road from Barrow, where our nuclear submarines, for example, are built. This is deposited in a special landfill site, one where concrete vaults um, contain the relatively low levels of radioactivity within it for long enough that it's safe. Intermediate level waste, then, which is machinery perhaps that's been dealing with um, a lot of radioactivity or with materials that have contained that radioactivity. This needs to be deposited far more carefully, deeper in the earth, in impermeable rocks with various layers, various barriers between this material and the environment. There's less intermediate level waste than low level waste. The problem comes, though, from high level waste. High level waste is only a tiny percentage of the total volume of material. But this is the stuff that's most toxic. It is extremely hazardous to life and to the environment. Not only that, but it also remains toxic for a very long period of time. Now, at the moment, this material is stored at the surface at Sellafield. It's vitrified, so it's encased in glass. It's stored in pools of water to cool it um, before it can be disposed of safely. There are currently about 80,000 cubic meters of this high level waste. Now, that sounds like a lot, but if you imagine a cube with the lengths of side 43 meters, that's how much material we're talking. By 2100, the cube will have grown, so it's about 78 meters on one side. Still, not a massive amount of material. The problem comes, though, from where we can actually store this. Now, to do this, we need to have a number of different barriers. So we need to have a physical containment is our first step to contain this within structures that we create, or containers, should I say, that we create to be able to uh, hold this stuff in. So that's our first barrier. So that might be for it to be vitrified, to be encased in glass, for that to be put in concrete or steel or even lead boxes, which then may be put into sort of steel outer container with grout or cement between. Once we have that, we then need to store those in a very consistent, uniform chemical environment. One that, for example, is alkaline to protect those containers. One that will absorb any radioactive nuclei that escape from this. However, those barriers, those human made barriers, have to last for an incredibly long period of time, far longer than anything we've been able to make to this day. We're talking about periods of times that are measured in maybe 100,000 years. Or to put it another way, 20 times longer than Stonehenge has been around. So creating a human barrier for this is going to be extremely difficult. It's also crucial to put it in a geological situation that will provide that containment as well. Now, the geological conditions here are ones where we have very little groundwater flowing, okay? Or if we do have water, that groundwater doesn't reach the surface. It's old, it's saline, uh, it doesn't really move. We need to have stability for this. Stability from any compaction, any tectonic activity. It needs just to not change. And then with some containing impermeable barrier around and above it to prevent, if there is any leakage, from that getting to the surface. And also, this has to be deep enough down that erosion or even human activity isn't going to get at it. So there's going to be a limited number of places where these conditions will exist. The Finns have done this by excavating an extremely deep set of caverns. You can see here this is a model of the caverns that have been dug. Putting these materials about 500 meters below the surface. There's a very long access tunnel with a very gentle incline for moving materials into this underground facility. And then there's a vertical lift that takes the people in and out. as you can imagine, this is an expensive business. Now, Finland is helped by its geology. Uh, the the geology of Finland is generally craton. It's ancient continental crust, uh, crystalline and stable. So the geology has been right for this. If we look at how this has actually been constructed, when we get down to the deposition level, we have the high level radioactive material, which is usually spent nuclear fuel, uh, put inside a steel container, which is then contained itself within a copper outer container. That's the tunnel that's dug um, is then drilled at the bottom to create a vertical uh, disposal cavern. The canister is lowered into that. It's then filled with bentonite, which is a type of clay. Once the bottom of those tunnels is all, once those disposal facilities are complete, the tunnel itself will be filled in. And those containers then, hopefully, will stay there undisturbed for at least 100,000 years, if not longer. It's an incredible amount of engineering to be able to dispose of this material. Now, Britain has its nuclear waste. You have this um, on your handout of Britain's potential repositories. The location of Sellafield is shown there, and we also then have a number of potential settings for these. There are actually 4 potential types of geology that we can look at. There's a couple of videos to watch which will explain these ideas in a little bit more detail. But let's have a look at the geology. The first of these are small islands, places that are separate, usually with low population densities, and may have very stable hydrological environments. You can see these are shown up on the west and north coast of Scotland. The second situation, shown by this dark shading, are where we have some of our ancient rocks, similar to the ones we've seen in Finland. Crystalline rocks, low relief terrain, usually ancient igneous or more likely perhaps metamorphic rocks. Again, the dark shading shows where that is, around the north coast of Scotland, the Outer Hebrides, coming down the east coast of Scotland there, Anglesey here in Wales. There are some places where we have these similar sort of crystalline rocks, but deep beneath the surface, shown by this vertical shading that you can see in sort of the east and the Midlands of England. And finally then, areas where we have sedimentary rocks with very low permeabilities. Clay rocks usually would have that hydrogeological setting, which might give us that bit of stability. This is shown by the sort of the large dots here. You can see that down the northwest coast of England, and then running through the south and east of England. What I'd like you to do is I'd like to annotate both the geology, the geological cross sections, to show the why these rocks would be useful, or why would they be suitable, should I say, for the disposal of nuclear waste. And I'd also like you to annotate the map, because it's not just the geology that we need to consider here. We can consider we have to consider the geology. You can't put this stuff in places where the geology isn't right. But we also need to think about the geography of it. Annotate your map then to show, the potential geographical problems of some of these sites. Anyway, have a go at that now. See what you can come up with. As we see a tunnel being drilled at Onkelo, and we have conclusions, of course, in Finnish. Let's sort that out. Getting the geology right for nuclear waste disposal is critical. This is something that we have to face. We have to find a location where the geological conditions are right to be able to dispose of the problem of high level nuclear waste. This is a problem that we have now, and this is a problem that will only grow in the future, even if we don't build that many more nuclear power stations. We still have this material to get rid of from existing power stations, from decommissioned power stations, and also from our nuclear submarine fleet. We can't export this problem to someone else. No country in the world is going to accept nuclear waste from abroad. It's a British problem that we need to solve. The question is, where should it go? Where should we put this? What's the potential solution for disposing of this extremely hazardous material? We can't just forget it. It won't just go away. We need a solution. What do you think that might be? We do need to talk about other disposal of other types of waste, but that's for another lesson. I'll see you then.